Hello again for lesson 2 about stars and chapter 19.1 continuing. So I hope you had a good research into the different parts that you might or might not be interested in to do with our universe and all the different parts of it. That really was an opportunity for you to go away and do something that's a little bit different to what you have to physically learn about. And certainly for the few sessions that we go ahead on now, we need to focus on exactly what you need to know rather than what you're just interested in. Now, clearly, you'll hopefully go away and do that research yourself, but we do need to focus on what you do need to know and what's on your specification. So we'll start with the history of the universe, and that starts with something called nebulae. So I've got a few notes just here that I'm just going to briefly talk about, but in essence, we need to look at the formation of a star that starts with interstellar dust and gas, and that's in terms of gravitational collapse, fusion of hydrogen into helium, and then I mentioned it last session about radiation and gas pressure, so that's from your specification. So we'll start with interstellar dust and gas clouds. You'll be able to look at in your book for a picture, but in essence, they're formed over millions of years. And there's really small gravitational attraction between all the particles of dust and gas that's there. And as they start moving over time, they move towards each other and we get a great big dust cloud. And as I said, it's mainly hydrogen, but we're talking absolutely huge. As bits get closer, you get this thing called gravitational collapse, and it accelerates the particles closer together. And as they become closer together, they become denser and hotter. That's our thermal energy. And if they get to a certain point, then they might start fusing. So we get something called a protostar before a star, and that was from GCSE as well, that was mentioned. And we only call something a star when we do get fusion occurring. So that's when two hydrogen atoms will join together to make a helium. Now we need really large temperatures for this to happen. We've got two protons that have positive charges, and to get them close to each other you need a huge amount of energy to encourage them to do so, to overcome that electrostatic repulsion from those positive charges. Whilst I said atoms earlier, what I should have said was nuclei. Apologies for that one. It's the nuclei that fuse together. The atom would include the electrons around the outside, but we're very much talking about the nucleus of the atom here. So if the temperature and the gravitational pull together is strong enough, then we do get fusion, and that's when we call it a star. And then once the star's formed, it becomes, it goes into equilibrium. You've got almost an explosion outwards, and that's called radiation pressure. But then you've also got the gravitational pull inwards, and you get two forces balancing out the radiation pressure from all these mini, I guess, explosions, if you like, that are happening, that's trying to radiate outwards. That's then balanced with the pull of gravity, because these things are so vast and so big, so massive, that you get just a ball of fire that's constantly in equilibrium. So once the star's formed, you then become into what's called the main sequence. So that's where our star is at the moment. It's just sitting there, releasing energy, but it's still big enough to keep that ball-like shape with the gravitational pull pulling everything back towards the centre. So our star's about 5.5 billion years old, and we'd expect it to probably last for about another 5.5 billion years. So it's about halfway through its life cycle. Really massive stars, well, you'll see pictures later, but they will, because they're so much larger, they have to fuse so much quicker to keep everything in balance. So they're only stable for a few million years, much shorter amount of time than something like our smaller star. And then when it runs out of hydrogen, fuel in its core, that's when the sequence carries on into the later stages of the life cycle of a star. So just to reiterate the aims here, formation of a star, again, you'll need to go away and just look at some diagrams of what's going on to find out more about what a nebula is, what we mean by gravitational collapse. Fusion, maybe you're a bit rusty on what we mean by fusion, so you might want to go and look at some GCSE notes on that, and then maybe the difference between fusion and fission. So just in case you're unsure, fission is spelled F-I-S-S-I-O-N, and that's what we have in nuclear reactors on Earth. And equally, you might want to go and see some pictures about radiation and gas pressure. So in your book or on Caboodle, this is now chapter 19.2, the life cycle of a star. So we mentioned how they're born, and what we now need to do is talk about how it ends. And there are different methods, or different paths, I guess, of which way a star will go, and that all depends on how massive it is. Now, when we say massive, we don't necessarily mean huge. The chances are it is big, but massive, what that means is how much mass it contains. And if it contains a lot of mass and therefore is massive, then that links directly to the gravitational pull inwards. So gravity and mass. So if we start for a low mass star, so note that your specification talks of a low mass star like our Sun, whereas at GCSE we might have called it a medium weight star. So because the core of stars with a lower mass is cooler than that of a more massive star, they do remain on their main sequence, so that's their adult life, if you like, for much longer. However, often after about 1 billion or so years, they do run low on hydrogen, and then they move away from the main sequence onto the next phase of their life. So our star will turn into a red giant. So red because it's in colour, and giant because it grows larger. And stars between 0.5 and 10 times the mass of our Sun will turn into a red giant. And what happens is the gravitational force becomes greater than the radiation pressure because there's less hydrogen. The core then gets smaller, it shrinks, and the pressure increases so that fusion can still occur, but in each shell around the core. Fusion does stop inside the core as it's not hot enough to fuse hydrogen anymore and overcome those electrostatic forces, and then the star will expand as each layer cools. So our Sun at the minute is white-yellow in colour, orangey, and it turns red, and that indicates it's getting slightly cooler. So white means hot, and then red means slightly cooler. And again, I've only given you very brief notes on a red giant. There's plenty of opportunity for you to go away and research a bit more about red giants. What I would just add, though, is that red giants, when they do expand, we expect our Sun to just stop short of Earth when it does expand. So it will likely engulf the first two planets, Mercury and Venus, but it's certainly going to be very close to Earth when it does expand. But that's in about 5.5 billion years, so we probably won't need to worry so much about that in our lifetime. After being a red giant, we'll then get a white dwarf. So eventually most of the layers of the red giant around the core will drift off into space, and that's called a planetary nebula. And it leaves behind the core, and that is the white dwarf. So that's really key. You get almost an explosion, a planetary nebula, and it's the core that gets left behind. So it's white, or it's a white dwarf because it's very hot, and it's called a dwarf because it's, in comparison, very small. But as before, no fusion will take place. So it is still hot, about 30,000 Kelvin on the surface at least, but it really has released the vast majority of its energy now, so no fusion does take place. However, there is this thing called electron degeneracy pressure, EDP, and because it's very small and gravity is still very much there, electrons get squeezed together. And again, similar to when we spoke about protons earlier causing a repulsive force, when we squeeze electrons together, they've also got the same charge, a negative charge, and they're also going to start repelling each other. And as they get squeezed together and then repel each other at the same time, it gets to a point where it can't get any closer to each other, so it stops the core from collapsing further. And Chandrasekhar came up with a limit, and he said that the electron degeneracy pressure is only strong enough if the mass of the core is less than 1.44 of the mass of our Sun. And then that becomes the maximum mass of a white dwarf. And if it's larger than this, it takes a different path. Now again, that's very brief in going through it. I strongly recommend having a little look at the Chandrasekhar limit and electron degeneracy pressure. And then when I do a live session, we can then go through any questions that you have. We will be talking about this again at a later point, because there's also something called neutron degeneracy pressure, and it's all similar. So there'll be some examples of this later. But in addition to that, there's this thing called the Pauli exclusion principle, and that's also linked to EDP, that electrons can't be in the same place at the same time. So if you're squeezing these electrons together, as the pressure's so big, you can't force two electrons in the same place. So you limit the size at which the white dwarf can be. With stars bigger than our own, or more precisely, 10 times bigger than our Sun and more, then the evolution of a star is slightly different. So as the specification says, we get a red supergiant and then either a neutron star or a black hole with a supernova. Now there are other forms as well, but these are the ones that our specification go for. So if the mass is greater, that means it's much hotter, and as I mentioned earlier, it's fusing hydrogen far quicker. But eventually we do get a collapse like before, once all the hydrogen has then turned to helium. But since the cores are much hotter, the helium formed can overcome electrostatic repulsion and then form heavier elements in its core. So a bigger star will be able to fuse larger elements far easier, and that's where we get a lot of our heavier elements from, and then even more once we get to a supernova in a moment. So fusion here can continue until the core, we believe, turns into iron. Now, when you see this with nuclear physics, that gets to a point here with the binding energy per nucleon where it's just no longer energetically feasible, possible to release energy when you start fusing iron. So when you fuse the lighter elements, you can release energy, but iron is at the peak, so you can't carry on. So it continues until you get to iron, and then these reactions cannot release any further energy. And like before, when you get an unbalance of energy, the radiation pressure and the gravitational pull, so in this case, the energy isn't being released, so it becomes very unstable. and the star then goes into supernova, and the star collapses on itself. And the supernova, in the huge explosion, you'll be able to look at some pictures on the internet of this. They're the pretty ones that you often see. That's where the heavy elements are made. So all the heavy elements on Earth, bigger than those that you can see labelled here, will have been made in a supernova that then later have landed on Earth. So then after that stage, supernova, big explosion, leaves behind the core, and it will either be a neutron star or a black hole. So if the mass of the core is greater than that 1.44 limit, then it will turn into a neutron star. And given by the clue, it is mostly made of neutrons. It's really tiny as well, much smaller than you maybe imagine. And at the same time, also very, very dense. So if the remnants of the core is about 3 times that of our Sun, this gravitational collapse will continue, and that's when you get a black hole. So the gravitational forces are so strong that not even light can escape. And they're thought to be at the centre of most of our galaxies. So what you'll now need to do is just go through using the internet just to focus very much on some other characteristics of neutron stars. You can find out some really interesting facts about how dense they are and how it compares to Earth, if you like. There's quite a number of facts on that. And also loads of information about black holes. There's something called Hawking radiation that you may be interested in looking at. And the evidence, if you like, for black holes. Until recently, I think we thought maybe they exist, but maybe they don't. You could even find out some distances away that maybe our nearest black hole is thought to be, etc. So there's plenty of research that you can do just to add to that breadth and depth of your knowledge on these topics. But before you do, it might be useful to see how all of these things fit together. So I'll quickly go through a brief outline again, but just in a more pictorial format so that you can see where it all fits together. So we started right at the beginning with our nebula. That's that cloud and dust that over millions of years grouped together, and then gravitational collapse caused a protostar. Most protostars would just fizzle out, but if they get hot enough and they're the right conditions, then fusion starts, and we then get a star that sits in its main sequence for the majority of its life. So we'll go down this route first. So the small weight stars like our Sun. So they last for roughly 10 billion years, turns into a red giant, and won't last quite as long as a red giant, thousands of years, up to a billion-ish years. They're a lot larger, so the energy to keep the forces balanced, that radiation pressure versus gravitational collapse, the heavier elements run out as time goes on, and then eventually those layers drift into space, and that's called a planetary nebula. And then the core at the middle of the red giant is left behind, and that's called a white dwarf. And then white dwarfs, that's if the core is less than 1.44 of our solar mass. So that's the Chandrasekhar limit. So the pull in, the electrons repel the collapsing force in, which stops it from getting any smaller. But the magic number, 1.44 of our solar mass. That's the core that's left behind. And then the white dwarf will eventually fizzle out, but you need to know up to white dwarf. However, a star much larger will take the other path. Notice 20 and 10, that's not necessarily the important bit. This side is billion years, this side is million years, so a far shorter amount of time. It's easy to assume 20 is bigger than 10, but you really need to appreciate the million versus the billion. So if it's a lot larger than our sun, then it will be about 20 million years until it turns into a red supergiant. And these ones last, again, because they're a lot bigger, a lot less time. And then once all of the reactions have happened, if you like, and then you've got those iron rings that was mentioned in the textbook, certainly, and then you saw the picture earlier, you get a great big explosion, and it's sort of like an implosion explosion. There are different types of supernova. The one that you need to know about is what's called a type 2. But again, just in name only, you need to be aware, but a great big explosion, and that's where the heavier elements are formed. And now it depends on the size that we started, depends on then if it's a neutron star or a black hole. So the explosion, implosion, explosion, the explosion is the supernova, and then the implosion part is the core that's left behind. So cores above 1.44, so this side was up to 1.44, this is above 1.44 of our solar mass. That then turns into a neutron star, but this is where the electrons and the protons fuse together to make a neutron. And if it's larger than 2 to 3 solar masses, then that's when you get a black hole. And you've got this thing that I mentioned earlier, electron degeneracy pressure here, but here is neutron degeneracy pressure. So you then get the neutrons being pulled together, and then that makes something really dense, which then stops light from leaving. So that's the end of today's session, and we've gone through the majority now of 19.1 and 19.2. If you have any questions, queries, as always, please feel free to write something on Teams or leave a message on Show My Homework, and I'll do my best to get back to you. And I will also arrange a time when I can be available live online to answer any of your questions. But do put questions on Teams, on the stars or space channel that I've created, and we can try and answer your questions as quickly as possible. In the meantime, other than just doing the research around the topic and looking at the key things, please do have a go at the summary questions and take a picture of the work and send that in to me, and I'll be then able to give you some feedback or answer any questions that you may or may not have. So these are the questions at the end of chapter 19.2.